Hello everyone, in this video we will be solving problem 331, verify pre-order serialization for a binary tree. The problem statement is, one way to serialize a binary tree is to use pre-order traversal. If it has a null value, we record it using a sentinel value such as hash. We need to check and validate if the given string is a valid binary tree or not. One thing to note is we are not allowed to reconstruct the tree. So we need to solve this problem without building a new tree and then doing a validation on it. If you look at this example that is given, this tree that starts with 9 and then 32 as its child can be represented using the string 934 hash hash and etc. The basic idea is if there is a value in the node, we take that value and add it to the string, and if there is no value, we mark it as hash. If you look at node 4, there is no child nodes to it. So the next two elements in the string are hash and hash. Versus if you look at node 2 has only the right leg. It does not have a left one. That's why after 2, you can see just one hash and then a 6. Let's switch to the whiteboard and talk about how we can solve the problem. Let's use the same example given in the input. Let me build the equivalent tree for this input, and then we can try to identify the pattern between the two to solve the problem. So for this input, the tree would look something like 9. Then because it is a pre-order traversal, I will go to the left. 3, I will continue 4. Now I have a hash here, which means it's a null. So left leg of 4 is null. Again, there is a hash. So the right leg of 4 is null. I will traverse a layer up. So I'm back to 3. The next number is 1. So I'm adding that. After 1, there are 2 hashes. Left and right leg for 1 is null. I will traverse up to 3 and to 9. The next number is 2. And then after 2, there is a null. So there's going to be no left leg to 2. I will go to right. I have a 6 here. So building a 6. And then after 6, I have 2 nulls, which means 6 will have no child nodes. As you can see, it is a valid tree because we were able to build it with the pre-order logic. Now let's try to identify a pattern. If I wanted to find out the number of count of nodes that I need to add at each step, every time I'm adding a new node, I am expecting 2 nodes after that, a left and a right. But if I'm adding a current node, I need to decrement that count as well because I'm also counting it against the nodes that I have already counted before. What I mean by that is, if I am going to be iterating through all the nodes one at a time, I can determine how many slots or how many nodes I should expect in the remaining input to validate if this input is correct or not. Let's start with an example. So I will have a loop running. I will call my count of expected nodes as C. Okay. By default, I'm expecting one node to be there. When I'm pointing at 9 for start, so I will first start with decrementing my node because I've used a one node. If I were to just look at node number 9 and only this is the input, this is a valid input so far. So C will become 0. Now, if this is not the last node, let's say there are more nodes after that, I need to check if the number that I'm reading is a valid number. When I say valid number, it is not hash in this case. If it is valid, it means I am expecting 2 more nodes in the remaining of the input to make it valid. So if I'm getting 9, I should be expecting 2 nodes after that. So I should increment my C by 2. So my C will become C plus 2. So my new C value will be 2 because I decremented 1 before and then I'm incrementing 2. So after going through 9, let's increment our counter and point to the next number, which is 3. When I'm pointing to 3, I have to first do a decrement. So my new C value after decrementing will be 1. After 1, I need to check if the number is valid or not. If the number is valid, it means I'm expecting 2 more nodes after that. So I will do an increment of 2. So C is equal to C plus 2. So my new value will become 3. Okay, because I decremented 1 and then I'm adding 2. Iterating my index counter. So now I'm pointing at 4. It should be the same loop where I'm decrementing C by 1, and then because it's a valid number, I'm incrementing it by 2, which gives me the value as 4. If you look at the nodes that we have covered, we have gone through 9, 3, and 4. And if you want to identify how many nodes we will have to build to make it a valid binary tree, we can easily say that we will need 2 nodes for 4 left and right, 1 node for 3, and 1 node for 9, which are 4. So this is how you can validate manually and confirm if you are in the right track or not. To make a tree valid, we need to have both a left and a right node. 4 is the minimum number of nodes that we need to make this part of the binary tree valid. I hope you were able to understand how that C value is important in identifying if the tree is valid or not. So after going through 4, the next is a hash. Hash means it's a null. So I should not be expecting 2 child nodes after that. So I will only do a decrement on C, but I will not do a increment of 2 because it's not a valid number. So my new C value is 3. Now I'm pointing at this index, which is a hash. So again, I will go through the process. I will only decrement my C counter. Now my new C value is 2. Now we are pointing at the next number, which is 1. 1 is a valid number. So as part of the flow, first we need to decrement C by 1, which will give us 1 as a total, and then check if the number is valid or not, which is valid in this case. So we will increment it by 2. So my new value of C is 3. So after 1, I have a hash, which means only decrement my counter. So my new counter value will be 2. And again, I have a hash after that. So decrement my counter by 1 more. So now my new value is 1. So now after that, the next value in my input is 2, which is a valid number. So first decrement my counter by 1. So my new C value is 0. Because it's a valid number, I need to add it by 2. So my new value will be 2. I am at this spot. After that, I have a hash, which tells me it's a null. So only decrement my C value. So now it will become 1. No need to increment the 2. And the next value after that is 6, which gives me a valid value, which is a valid value. So decrement by 1 and then increment by 2, which will give me 2. And after that, I have 2 hashes. So I will decrement my C by twice, 1 and 1. So at the end, it is 0. The end validation is to make sure that the value of C is always 0. Only then we can say we have a valid binary tree. If C is anywhere greater than 0 or less than 0, we need to throw an error. At any given point of time, if C is less than 0, it means that the input is invalid. We need to return false. The time complexity of this problem is O of n because we are iterating through all the numbers once, and our space complexity is O of n because we are going to be splitting this input into a list or mapping it to a collection and then iterating through each and every entry. Now let's look at the equivalent C# solution. Here is the C# implementation for the approach that we talked about. In the main method, as valid serialization, I start with having a variable called count, which is set to 1, and then I iterate through all the items in the pre-order list after splitting it using the comma. So comma is my separator. For each item, I start with decrementing the count by 1 because each entry is actually a node. Then I have a validation checking that if my count is less than 0, it means I have an invalid pre-order traversal and return false there itself. If the validation passes, then I check if the item is not equal to a hash, which means it is a valid number. Then I increment my count by 2 and then continue the loop. After the iteration is complete, if my count is 0, I return true, else I return false. Thank you for watching this video. I hope you were able to understand this approach to solve the problem. I will be adding the link to this source code in the description below. Feel free to check it out, and I will see you in the next video. Thank you.